Hello all. So once again, I'm here with machine 2, and although you have requested and I have tried, but you know what happened, and I hope you all of you know that what happened and why I am here again to disturb you. Anyway, so let us start. And today I'm going to start discussing characteristics of synchronous generator. So it is needless to say that those who have not studied fundamental of rotating machine and have no idea about that fundamental of rotating machine will not able to understand a bit of this lecture. So in that case, I request you that please do not waste your time and go and watch the fundamental of rotating machine first and then come and watch this video. Otherwise, again, means it will be a wastage of time. So today our topic of discussion is characteristics of synchronous generator. Now here, as we will first start with cylindrical rotor generator. We will get open circuit characteristics, short circuit characteristics, and zero power factor characteristics. What are they and why they are required? I am going to tell you one by one. First of all, how can you obtain open circuit characteristics? It is very easy. I am doing, or rather drawing a very crude schematic diagram of the connection of your open circuit test. What we do here, it's very simple. Suppose this is my stator of the generator having three. We connect, we are assuming a balanced stator winding. We place a voltmeter between any two terminal, and here we have our field winding, and this one will read our field current and this one will read our induced voltage. And what we want to obtain a characteristics between our field current and induced voltage. Obviously, while doing so, we have to make sure the speed of the alternator should be uh, constant and should rotate at the rated speed. And generally, what we get that is very common and very means like quite often known to us, we get a characteristics curve like this. After a certain region in which it is behaving in linear, then gradually it becomes means we cannot see a proportional change in our open circuit voltage, and that is quite obvious because what this field winding current is going to do. Field winding that is embarked on your rotor is going to enhance or strengthen the field flux present inside your machine housing. And if you increase the field flux, actually you are going to increase the actually it is not actually going to increase the field flux, rather better to say it is going to increase the ampere turn of the rotor winding. So basically it is going to increase the H, and each is directly proportional with this field current. However, we know that due to the iron after a certain value of mmf, or not only mmf, rather better to say after a certain value of magnetomotive field intensity, which is known as H ampere turn per meter, we get a nonlinear that our materials, magnetic materials, start observing or start exhibiting saturating characteristics. And therefore if we increase H beyond our linear region of operation, we will see that the change in B is not proportional to H. However, our induced EMF, that is being proportional to our flux, that is directly proportional to B. So whatever change or whatever flux variation we can observe in our BH curve, the similar kind of variation we can expect here in our like in our synchronous generator output characteristics curve. This VOC, it is directly proportional to your flux or your flux density B, and your flux is however maintaining a nonlinear relationship with your H, or H which is directly proportional to this current, that is IF. So that is why we are going to get this kind of relationship. I do not know whether this is a blessing or a curse on you, but in this semester you will realize that the book of Thereja or other books that are quite suitable and in my opinion somewhat good for diploma student will not be sufficient to provide you the adequate amount of information or knowledge or numerical problems that you can expect in your semester examination. And I have already posted text in your MS Team group, but likewise you people are very reluctant and very indifferent to my text and have not yet replied anything. Right now it is 9:26 p.m. 15th December 2020, but I couldn't hear it from you, although I have posted that text around around 1 p.m. or something. Anyway, that is your choice whether you would like to face the examination for entire 80 marks or want a 20 marks grace, and for that you want to appear in class test. That is your choice. People are quite senior and mature, means at least should have maturity to understand this. Anyway, let us move to the next one, that is our short circuit characteristics. What we do in case of short circuit characteristics, we just short these terminals and place one short any two terminal with a solid conductor and short the another remaining two with an ammeter. Here we are assuming that this ammeter is having zero resistance, and what we get that our machine almost gives us this kind of characteristics, linear characteristics. Here there is no saturation is being observed. Why so? It is interesting to note that in case of your short circuit test, if you have read the armature reaction part of your fundamental of rotating machine, you must have understood that when you short the armature terminals, it will produce a very high demagnetizing MMF that is sufficient enough to counterbalance the MMF produced by your main field winding IF, and therefore even if you are going to increase this value here, the current through your armature terminals are continuously increasing, and we will increase the field current till this ISC reach 125 to 150% of its full load value. So if it is full load value is 10 ampere, then we will adjust this IF so that this reach 15 ampere. Obviously IF, don't get confused that IF will be 15 or 10. IF is being the field current is generally limited for small machine. It is if it is 10 ampere its full load value, then it is, you can expect it like in the range of 0 to 1 ampere, the maximum variation of IF 1 ampere. So when you, but we don't means we do not consider here how much IF do we need. What we need is that we will ensure the rotation of our machine. This one is exactly similar to your short circuit test, where you do not care about how much voltage do you apply across your high voltage winding. What you care while conducting the short circuit test is the amount of current that is flowing through your primary side winding or high voltage winding. In case the primary side winding carrying, you find that primary side winding carries 125% or 150% of full load current, then you stop increasing the voltage. So the same thing you can understand here, that we do not we do not vary IF based on value or magnitude of IF. Rather, we are interested to observe the variation of ISC, and as soon as ISC reaches 125 to 150% of its full load value, we stop means change of IF. Otherwise, if you continue to increase the value of IF beyond that value, your machine will burn out. Now, another thing, that is zero power factor characteristics. I'll come to that, but before that, we need to construct a model of or a model to represent our synchronous machine. Now, this model, what type of, like, we have certain idea that when we are considering or we will try to draw, if you have watched the fundamental of rotating machine carefully, then you must have noticed that in some video I have made a comment that a synchronous machine is like a generalized transformer. So what is playing the role of your secondary? Obviously, your stator winding or your armature winding is going to play the role of your secondary. And what is your primary? Your primary is your field winding that is rotating, but field winding carries DC current, but due to its rotation the stator winding exhibits a flux variation, and therefore a voltage is getting induced across your stator winding, and that voltage ensure a flow of current through your stator winding. Now here it is one thing I would like to make very clear and very specific, that in case of your transformer, what is the difference? We need to remind ourselves about the difference between transformer and this synchronous machine is that in case of transformer, as your primary side is connected, generally connected with a merely constant voltage source, therefore what happened that in case your secondary produces demagnetizing MMF, and as soon as the primary side realizes there is a demagnetizing MMF produced by the secondary winding, how it realizes it in this way, that whenever the demagnetizing MMF of secondary winding causes a net reduction in your core flux, suddenly primary winding understands that it needs to draw more magnetizing current to maintain the net flux constant. Why? Because the core flux, that is also the net flux of your transformer, both the winding, is directly proportional to your primary side voltage, and as your voltage, primary side voltage, is almost constant, so there is no choice other than drawing more magnetizing current and make sure the voltage remains constant. That is why we sometimes also say that transformer is a constant flux machine. However, in case of synchronous machine, what happens that there is no such bound on your rotor or the magnetic field winding. This rotor is connected with a constant DC voltage source, and the amount of current flowing or circulating through your rotor winding, that depends on your this resistance setting. If you set a particular value of current, whatever be the demagnetizing effect produced by your armature winding, this current almost remains constant. So unlike transformer, that the primary automatically draws some more current to counterbalance the demagnetizing effect, here in case of synchronous machine there is no such provision that synchronous machine rotor winding can draw more current to counterbalance the demagnetizing effect, and therefore we must consider the case of demagnetizing, and that is how the secondary of a transformer equivalent circuit is considerably different than that of the electrical equivalent circuit of a synchronous generator stator winding. I hope I'm correct, means clear. So what I was trying to tell you, that is very simple thing, that when we will try to model, if if you can recall the modeling of transformer, like we do not know what is there inside transformer, but just from ideal transformer we try to understand that, okay, if we replace the ideal conductor of transformer winding by a practical conductor, then winding resistance can come in to picture. Similarly, like when we consider that all the flux produced by the primary winding doesn't link with the secondary winding, then we consider that now the aspects of leakage inductance will come in the picture. But here what is means what we must understand that how to model that component that is responsible for demagnetizing of this uh, means some electrical equivalent component that is responsible for this proportional demagnetization of our. Now, instead of trying to explain you in verbally or in some other way, let me draw the phasor diagram very clearly, and you will understand that what happens. Before I draw the phasor diagram, I would like to tell you that I hope you still remember I told you that the cause and effect relationship, and that cause and effect relationship which we consider during construction of phasor diagram for transformer, that the cause always lead the effect by an angle of 90 degree. So here if you consider the cause, then obviously cause is the rotating MMF produced by your rotating field winding. And what is the effect? Effect is the induced EMF. So obviously it is means needless to say that induced EMF should lag behind your rotating MMF by an angle electrically equivalent to 90 degrees, right? So let us draw the phasor diagram, and I hope that construction of that phasor will make many things clear to us. So let us consider that here our machine, we have connected a balanced three-phase load with a power factor of, say here a load is connected and the load power factor is theta. That means if you measure voltage V here and current IA here, then the angle between V and IA is theta. So just considering that they are the secondary of the transformer, what you can draw is like you can have, just a minute, just a minute, hold on a second, let me. This is our, sorry, this is our V, and now we have an IA. This much is angle theta, and if we consider the armature winding comprises of, or means rather not comprises, rather electrically they can be represented by a combination of resistance and leakage inductance, then for this IA amount of current flowing through this V, we can find out the amount of voltage drop that actually takes place here. So what we get here, that is, so let this be the induced voltage across our armature winding. So with this, what we are getting, this E. Now obviously when you are having this armature current IA, this armature current will also produce an armature MMF that is denoted by A. What is A? A is your armature ampere turn. Now this A should maintain the same phase or same orientation with IA. Now if this is our E, this E is the voltage E induced across our transformer winding. So transformer winding, if we just based on our previous knowledge, we consider transformer winding comprises only two components. One is leakage inductance, that is XL, and another one is RA. Fine. Then here we are having E, here we are having V. But do remember, this E is generated by what? This E is generated by the resultant MMF rotating in your, like what I am trying to say, if your field current then this F naught is constant. Now this armature MMF is variable and proportional to your IA, and the resultant MMF Fr, that is equal to F plus A. Now when your machine is supplying a load that is having power factor angle theta, and the IA amount of current is drawn by that load, and your machine is maintaining a voltage V across that load, then you are getting this. Now if you follow that cause effect relationship, what you can draw a corresponding MMF that is exactly proportional to this E. Here we are assuming a linear circuit relationship we are not considering any nonlinearity present in the machine, because if we consider nonlinear, if you still recall my first few lecture on phasor diagram, you will be able to remember that we cannot represent any nonlinearity in our phasor diagram. So just let me erase all this. So what we will have, this f we can write from this should be f naught actually. F naught is fr minus a, right? So we can draw minus a on this fr. Actually, I have drawn armature reaction, a slightly higher value of armature reaction. Generally, armature reaction is not this high, like so. If this is our fr minus a, so let us draw minus a. If this is a, then minus a will be exactly 180 degree out of phase. And if we join them, then we will get f naught. Now what we are means, as we have assumed that our circuit is linear, so obviously the mmf and induced emf should be maintain a proportional relationship. Like what I am trying to say, that these E and fr are proportional. Now if they are proportional, then obviously we can have another emf E naught proportional to this f naught. This E naught we can find out from our open circuit test. E naught represent our open circuit induced EMF. So this E naught should be now. Once you draw this E naught, then you will find that E naught and E, they are having a considerable amount of voltage gap exists between E naught and E. Now the obvious question that will come in your mind, that how we can represent this drop. Like I'm talking about the drop between these two. How or what type of electrical element should we consider here? Like more precisely, if I try to adjust them in this diagram, then we will have E naught here, and here what is the element? IA is flowing in this direction. Now what is the element we should draw here? A resistor, an inductor, a capacitor, which one? So in order to understand that, what we need to do, we need to take help of basic geometric analysis. Let us just join the tip of E naught and E. Once you join the tip of E naught and E, then what you will observe that this E naught, these two sides are like E naught is proportional to F naught. Just a minute. Now here you can see that E naught is lengthwise proportional to F naught and E is lengthwise proportional to FR because we are assuming linear circuit. Now this angle is 90 degree, the angle between E naught and F naught, and the angle this one like FR and E, this one is also 90 degree. Now what we can write, this angle, like if we take from FR, this is 90, from F naught, this is 90. Now if we draw something like here, from F naught, okay, well, now these two are 90. Now let us see that what is the common angle that contains, or both the angle, okay, let me just write some so I'm talking about angle A4D, that is 90 degree. Then angle EOC, they are 90 degree, and both this angle contains which, or contain which angle? Both this angle contain angle EOD. So if we subtract this EOD from FOD and EOC, what we will get? We will get this angle, that is angle EOF is equal to angle COD. This we will get. So these two angles are equal. So what I am trying to say, that these two triangle EOF and triangle COD, they are similar triangle, right? These two triangles are similar. Now if these two triangles are similar, then obviously this minus A is proportional to this one, this length CD. So we can say that lengthwise EF lengthwise is proportional to CD. In addition, as these triangles are similar, we can understand that this angle is equal to this angle. Therefore, it is quite obvious that this CD is a collinear vector with this BC, or in other words, we can say that CD, this arm or this side of triangle OCD, it is maintaining a perpendicular, or means that is in exactly in perpendicular with this IA, because BC, we already know this BC or CB is perpendicular to IA. Therefore, this CD is also perpendicular to being collinear with this CB. This DC being collinear with this CB is perpendicular to your IA. Therefore, what we can conclude that here we have another fictitious reactance that is known as your, we can call it synchronous reactance, right? This synchronous reactance, it is very interesting to note that this synchronous reactance is not a physical one. Neither XL is also a physical reactance, but this X0 is also actual reactance. This is used to represent the drop caused by the demagnetizing ampere turn of your armature winding. So what we did, let me repeat it once again. In future I will not repeat or not move in such a slow pace, but this is the first lecture of this semester and I do not want that it itself be so strong and means repel you enough, so that in future, instead of watching any of my lecture video, you rush to read Theresia or other books, because unlike your first semester where mostly you got the things covered from Theresia, this semester if you consider the syllabus, only hardly synchronous and induction machine you can get it from Theresia, but neither the advanced machine nor the generalized theory of electrical machine. That is a considerable part of your syllabus. And also, please do note that why initially I decided to discuss DC series machine during your fourth semester, but I dropped it because in this semester we will have universal motor, and that is just an advanced version of DC series motor. So in order to avoid overlap also burden on you, I just discard that from your first semester, means third semester part, but we will discuss it in detail in this semester, right? Now get back to our topic of discussion, what I was discussing, that first of all we analyze the difference between a transformer and a synchronous machine, typically a transformer secondary and a synchronous machine stator. Then we consider that we are having a load of power factor theta connected with synchronous machine terminal, while the synchronous machine field current is so adjusted that we are getting V voltage drop across this synchronous machine terminal. Now, as we know that synchronous machine stator winding may always can always be represented by means of a resistor and an inductor. We consider that it contains only two elements, that is armature resistance and leakage reactance. How we can measure these elements, that that we will discuss later, but there are test methods which can help us to determine the parameters like RA and XL. So it is not a big deal. So once you know RA and XL for certain load current and certain value of load voltage, you can construct the phasor E, that is the induced voltage for that particular load at that time. Now for that E, following that cause effect relationship, what you can do, you can draw two MMF component. What are the two MMF component? One is your FR, that is the resultant of your okay, before describing FR, let me describe this A. This A is your armature reaction MMF. If you have forgotten armature reaction MMF, then that is very good. Blessing in disguise. Please go back to your third semester topic and watch some video of fundamental of rotating machine, where you can find it out. I forget it completely because it was long back and nobody asked me any question, but if you go back there, you will surely be able to locate a video that clearly describes in detail how we can calculate armature reaction for a certain value of stator current. Now if we can calculate armature current A, then we are having this what we can understand, that if our our field MMF, that is F naught, this F naught and A, they interact with each other and they produce FR. This FR is the resultant MMF rotating in your air gap, and this FR is solely responsible for production of your induced EMF E across your stator winding, and this E induced EMF across your stator winding, it's, as we have considered, that the total linear representation is magnitude wise proportional to the magnitude of FR. Now we cannot measure F naught either. What we can do is that we can draw FR. Now if you ask me that how to draw FR, if you know the scale of proportionality between your voltage or EMF and MMF, then from E you can draw FR, that is leading your phasor E by an angle 90 degree. Now if that is the case, then with that FR, if you apply this relationship, that F naught is equal to FR minus A, then you can construct the phasor F naught, and from that F naught you can, by using that similar proportionality same proportionality constant, you can construct the phasor for E naught exactly lagging F naught by an angle of 90 degree. After that, we will be curious how to represent the gap between E naught and E. What is E naught? E naught is that if you suddenly disconnect this load and make IA is equal to 0, keeping or ensuring your field current constant, then your machine terminal voltage will become E naught. Now, if we become curious to represent E naught, or rather we started looking for an element that can be placed between E naught and E. Then we started thinking and considering we have three elements like capacitor, inductor and resistor. We were like thinking about which one could suitably be placed in this gap. Then we analyze two triangles OEF and OCD and found that OCD and OEF are similar by virtue of their construction. As these two are similar, then we conclude that EF and CD, they are magnitude wise proportional. So once we understand that CD and EF is magnitude wise proportional, then using the geometry of this construction, we further realize that the CD and BC, these two vectors are collinear. Now BC being the voltage drop across your leakage reactance, it is bound to be perpendicular to your current IA. And if we find another drop across any unknown component that is collinear with the voltage drop across an inductor, then we can conclude that the unknown element is also an element of pure inductive in nature. So that unknown element which is present between E naught and E, that we conclude that it is it is not Jx naught, we term it Jx A. It is armature reactance, and when we add them we get the synchronous reactance, that is XL plus XA. This XA is known as armature reactance and XL is our leakage reactance. These two, when we add, they together represent a virtual reactance component known as synchronous reactance. It is very, very important for us, right? So this is what we can construct the Phasor diagram for our synchronous machine. This is also known as EMF method of Phasor diagram construction. This EMF method of construction is very, very important for us. There are another few methods like MMF method, modified MMF or American Standard method for Phasor diagram construction, zero power factor method. We will discuss all this in my next video. As this is the first video, I am keeping it for only 1 hour, since in last semester someone from your batch accused me for uploading numerous videos. Since then I have taken I made a commitment to myself that henceforth I will not upload video of 1 hour duration. Rather, what I will do, I will film a video of a complete module and upload it. Whether you find it convenient or inconvenient, I need not to be worried with your like ease of access or your convenience, because when that particular person accused me for uploading numerous videos, you didn't show any interest to raise your voice that no, uploading 1 hour video is good for us. So I hope you find this one agreeable, that if I upload a video on a module, whether it is of duration 2 hour, 3 hour, 4 hour, 5 hour, you will find it agreeable. Rather, you should. So this is our first video. This is known as EMF method, and what we can do, we can calculate the regulation. What is the regulation amount? The regulation amount is given as regulation amount. Let me write the regulation amount. It is E naught minus V by V. So the amount of regulation is so how we do it, like generally for a certain load current, we adjust our field winding in such a manner that our V or terminal voltage reach the rated voltage of the machine. So if it is a 400 volt machine, we adjust it in such a manner that this V becomes 400 volt, and then we disconnect the load and find out the E naught, and then that difference E naught minus V by V into 100, that gives us the regulation amount. However, do note that that is the experimental way to evaluate the regulation, but here what we try to do, we try to evaluate it using our analytical method, right? Like calculating E naught from all these based on this calculation, and what we observe that whatever regulation value we calculate in this way is higher than the actual regulation. Why so? Because in case of your actual machine, when you will go for F naught, E naught is no way proportional. It is difficult to realize E naught that is proportional to F naught, because generally our machines are designed to operate at the knee point of your BH curve. So F naught is quite, the F naught MMF is somewhat higher than the saturating MMF for your core. So your E naught is not actually become proportional to F naught, rather slightly less than the proportional. Like if you get something E naught dash that is exactly proportional to your F naught, in reality what you will get by disconnecting the load, that E naught of reality is less than that E naught dash that you should get by your theoretical calculation. So that is why this E naught, what you are calculating here based on the proportional relationship with F naught, is higher than this is theoretical one. So what we can write, that E naught theoretical is greater than E naught practical, and that is why it causes
a higher value of regulation. Here what we do, we replace a physical MMF, that is our armature MMF. Armature MMF is always a physical MMF, by means of a virtual EMF, that is the CD, across a virtual component, that is XA, armature reactance, where armature reactance is no way a physical inductance present in the circuit. So this method is known as EMF method. Okay, so I hope it is enough for you to get confused today. We'll meet in our next video.